In the previous web clip, I explained that there are three forms of polarization, apart from the unpolarized form of polarization. There is linear polarized light, where the electric field oscillates along a line. There is circular polarized light, where the electric field oscillates along a circle and where the component in the x and y direction are equal but out of phase. And there is the general form of elliptical polarization. In this web clip, I'll show you how to transform one form of polarization into another by using birefringent crystals. Birefringent crystals are crystals that are anisotropic, that have an anisotropic crystal structure, which means that the forces between atoms and their neighbors can be different in one direction than in the other direction. And it also means that the oscillation frequency of atoms oscillating in one direction can be different than that in another direction. This anisotropy has two consequences. On the one hand, it produces polarization digorism, which is a fancy word of saying that the optical absorption of light with one type of linear polarization can be different than the optical absorption for light with the other linear polarization, just because the atoms oscillate at a different frequency in one direction than at another. And of course, if the atoms oscillate at a frequency closer to the frequency of the light that you use for illumination, then the absorption is larger. A second consequence of anisotropy is birefringence. And with birefringence, I mean that the refractive index for light in one polarization can be different than for the other polarization. So you can have a situation where the refractive index for light polarized in the y direction is different for light polarized in the z direction and different for light polarized in the x direction. This is the general case, but in many crystals, the anisotropy is such that the refractive index in two directions is the same and only in one direction it's different. And you call these uniaxial crystals, and you call the funny direction, the extraordinary direction, the z-axis. So you talk about polarization, ordinary polarization in these crystals, which is a polarization either in the x or in the y direction. And you talk about extraordinary polarization, which is a polarization that has a component in the z direction or along the z-axis. Finally, a cute picture of a birefringent crystal, a picture that I also show during the lectures. If you look through a birefringent crystal, you see a double image. You see that the light of one polarization propagates in a different way than light at another polarization, like sketched here in a side view. And as a consequence, you see a double image for, say, one polarization, X polarization, and Y polarization. Birefringent crystals can be used to make polarizers if they're cut in a funny triangular shape and glued together. This slide shows you two examples of such polarizers, a nickel polarizer and a Wollaston polarizer. And I won't go into the details, but let me roughly sketch what happens. You have two triangular shapes, and these shapes are cut from a crystal, a birefringent crystal, with axes aligned in a different way. In the axis here, the z-axis, this funny axis, extraordinary axis of the birefringent crystal, is indicated here with these lines and here with these lines. So you see that the z-axis is in a different direction in one triangle than in the other. And as a consequence thereof, the propagation of light is in one of these triangles ordinary, for instance, and in the other triangle it's extraordinary. So you switch from ordinary to extraordinary. And you can use that in various ways to produce a polarizer. For instance, in this nickel polarizer, one of the polarizations is such that you go from a high index to a low index material, and you have Snell's law here at the interface, and a slight refraction. The other polarization, however, is already bent here in a slightly different way because of its different index. But then at the interface, it goes from a high index medium to a low index medium, and you can potentially get total internal reflection. So you can, in that way, remove one of the two polarization components, and in transmission only keep the other component, in this case the extraordinary ray. For Wollaston polarizer you use a similar trick, but now Snell's law is not beyond the critical angle, it is just Snell's law. And again, one of the rays going from low to high index medium bends towards the surface normal, and the other ray going from high to low index bends away from the surface normal here. And in that way you get two beams out of the polarizer. One with one polarization, ordinary polarization in this case, and the other with the extraordinary polarization. Propagation through a birefringent crystal can modify the optical polarization, which is sketched in this figure. So we start with linear polarized input as an example, and we take care that the linear polarization is at a certain angle with respect to the fast and the slow axis of the birefringent crystal. Fast axis meaning the axis for which the light propagates fast through the crystal, so has a low refractive index, and slow axis meaning the axis for which the polarization in that direction propagates slow through the crystal, so has a high refractive index. And to understand why propagation through a birefringent crystal can change the polarization, we need a little bit of math. So what we do is we'll start with this linear polarized input and decompose it along what we call the x and the y-axis defined by the birefringent crystal. And if you can decompose the field, it of course has an x and a y component with an amplitude depending on this angle, and the oscillations in these x and y directions are in phase because we started with linear polarization. Now if you propagate this light over a certain distance d, upon propagation you acquire a phase delay just because you need time for the propagation. And the important part to note now is that this phase delay is related to the product of the wave vector times the thickness of the crystal, the propagation distance through the crystal. And this wave vector is 2 pi over lambda, but it's lambda in the medium, which means it's the vacuum lambda divided by the refractive index, and because it's in the denominator you get it here in front. So if the refractive index for one polarization differs from that of the other, this phase that you acquire upon propagation for one polarization will also differ than that of the other. And to clean up this expression, you can introduce a new time, shift it with respect to the old time by the propagation time through the crystal for one of the two polarizations, and then you find that the field at the output has, if you decompose it into the two components, slow axis, fast axis, the amplitudes along these axes of course do not change, but one component one of the polarization components acquires a phase delay with respect to the other, because it propagates at a different speed. So the crucial parameter to quantify the behavior of plates of birefringent material, so-called wave plates, is the phase retardation, the relative phase retardation between one polarization and the other. A relative phase retardation which you can write in this way. And so which depends on the index difference between the two polarizations, the thickness of the crystal, and the wavelength that you use. Now we distinguish two different types of plates, which are the most convenient types of plates to use. On the one hand, we have quarter wave plates, where the difference in optical path lengths for the two polarizations is precisely a quarter of the wavelength in vacuum. And so where the phase delay between the two polarization is pi over 2, 90 degrees. And with this plate, you can transform linear polarized light into circular polarized light. Because when you start with two components which are in phase, then after propagation, they're 90 degrees out of phase. So you go from linear to circular polarized light. The second type of useful plate is the half-wave plate. For a half-wave plate, this difference in optical path length is half times the wavelength in vacuum. The phase delay, relative phase delay, is pi, and this plate enables you to transform linear polarization into another linear polarization, but one that is rotated or mirrored, as you'll see later. Now next, I'll give a demonstration of the action of birefringent crystals, of the changes in the polarization in birefringent crystals, using a funny type of pendulum.
This is a demonstration of the effect of birefringence on the optical polarization of light when it propagates through a birefringent crystal. That is, a crystal which has a different speed of propagation for one polarization than for the other. And I'll demonstrate this with an equivalent, which is a bipendulum. As you see, it's a pendulum, but attached to the ceiling in a somewhat funny way with this triangle. And the result of that is that the oscillation in one direction, this direction, has this point of attachment, and that length of the pendulum is smaller than the pendulum that you get for oscillations in the other direction, where the point of attachment is higher up. So these two oscillators, oscillator in this direction and that direction, have a different eigenfrequency, which means that in time they'll run out of phase. In a similar way as light propagating through a birefringent medium, one polarization runs out of phase with the other upon propagation. So that's the demo you will see in a minute. So let's see what happens on the floor. If we excite the oscillator in one of its principal directions, you see it's a pretty boring pendulum. Oscillations to and fro in one direction. But this demo becomes really interesting if we excite the pendulum in two directions simultaneously. So in this direction and this direction. You see, you start with a linear oscillation, but in due time, the oscillator in this direction and that direction get out of phase, and at this point they're 90 degrees out of phase. You see a circle, and if you wait longer, they're 180 degrees out of phase. And you get a linear oscillation in the orthogonal direction, along the other diagonal. And if you wait longer, you slowly get a circular oscillation again, but now in the other direction. Now clockwise instead of counterclockwise. And You return to the original oscillation, linear polarized, 45 degrees, you wait, circular again, wait longer, linear in the other direction, and this demonstration of the bipendulum in time demonstrates the effect of changes in the optical polarization upon propagation through a birefringent medium, where also you change from linear polarized in one direction to circular, to linear polarized in the other, to circular, etc. At least for the right type of polarization excitation.
I'd like to finish with two examples of the action of wave plates to see whether you understand their action and to demonstrate their performance. So in the first example, we consider quarter wave plates. And we illuminate a first quarter wave plate with left-handed circular polarized light. Well, a quarter wave plate allows you to transform circular polarized light in linear polarized light. And it does it in the following way. You decompose the incident circular polarized light into its two components along the slow and the fast axis of the crystal. For the incident light, these two components are 90 degrees out of phase, but after propagation through the crystal, you acquire an additional 90 degree and they are 180 degrees out of phase or in phase. But which either way, you get linear polarized light out. And in this example, that light passes through a linear polarization, a linear polarizer, if only to demonstrate that it's linear polarized. So intensities shouldn't change from this one to this one. And then finally, you go through a second quarter wave plate, but now one rotated at 90 degrees. And this quarter wave plate has its axis at 45 degrees with respect to the linear incident polarization. So again, you have to decompose into equal components along the fast and the slow axis. One acquires a phase difference of 90 degrees and you get circular polarized light out. And as a final point to note, in this particular case, the light you get out is again left-handed, and basically because the second quarter wave plate was rotated by 90 degrees with respect to the first one. So if this is the slow axis of this plate in the y direction, of the second plate, the slow axis is in the x direction. If we wouldn't have rotated the second plate, if the second plate would have its slow axis also in this direction, then the outcome of this experiment would not be left-handed light, but would be right-handed light. Basically, you might say, because if you have a quarter wave plate here and a quarter wave plate here, together they act as a half wave plate, because this intermediate polarizer can also be removed. The polarizer didn't do anything because it had its transmission axis in the direction of the linear polarization that we had in front and in the back. As a final example of the use of polarization components and wave plates, I'll show you that the combination of a polarizer and a quarter wave plate oriented at 45 degrees with respect to the transmission axis of the polarizer can act as an optical isolator to isolate any input from reflections. And the working principle is as follows. We start with randomly polarized light incident on a linear polarizer, and of course the polarizer transmits only one of the polarization components, one linear polarization components. Then we have a quarter wave plate oriented at 45 degrees, which converts this linear polarization into circular polarization. Say it's oriented in such a way that the circular polarization is right-handed. Now we reflect that light from a mirror and wonder what happens to the handedness of the polarization. In real space, normal orientation, X, Y, Z, nothing happens. I mean, the circular polarization, you might say, sort of excites charges on metallic mirrors in a circular way. These things move circular and they emit light with the same circular nature. But for light, if you talk about the handedness of light, you mean the handedness of light with respect to its direction of propagation. And when light reflects, the direction of propagation changes, inverts. And hence, what used to be right-handed polarized light and still oscillates in the same way in real space has now become left-handed polarized light. Very important. And if you continue follow the propagation of this left-handed polarized light through the quarter wave plate, you'll see that at the output of the quarter wave plate, the light is again converted from circular polarized light to linear polarized light, but now the orientation of this linear polarized light at this point is out of the plane, is at 90 degrees with respect to the polarization we had here, which means that this light is fully blocked by the linear polarizer. So a cute way to isolate reflections, because any reflections you had from the mirror, sometimes spurious reflections you want to remove in an experiment, you can remove by this combination of polarizer and quarter wave plate. A final note. It looks complicated, this transition from right-handed to left-handed, or it might look complicated. You can also look at it a different way, at this isolation. I mean, the light basically goes through the quarter wave plate twice. First from left to right, and after reflection from right to left. So effectively, going twice through a quarter wave plate is the same as passage through a half wave plate. And for a half wave plate, you know that if you have one polarization, if you start with linear polarization in the y direction, and if the half wave plate has its axis oriented at 45 degrees with respect to this input polarization, you have to decompose along the slow and fast axis. One of the two components gets a minus sign because it is half wave, it's 180 degrees retarded, and then if you combine the two, you get the other polarization. So this half wave plate allows you to transform linear polarized light from the y direction to the x direction, what I called mirroring in the previous slide. So another explanation why this combination of polarizer and quarter wave plate can act as an optical isolator. I thank you for your attention.